time. All right. Good morning or good afternoon. This is Dynamic. We have a new chapter, chapter 14. It's the work of a force, the principle of work and energy, and system of particles. This chapter talks about the energy method, which is an alternative method for solving dynamic problems. Especially, it concerns with problems that highlight the velocity, distance, and forces acting on a particle or a system of particles. So today we'll learn what is work of a force, what is the work on a particle, what is the work of weight, and the work of a spring, and the work of external force. What is the principle of work and energy, and how to use it in different problems. Now, the answer for the first reading quiz is that, or the question is asking you, what is the work done by the force F, where the F is perpendicular to the displacement or to the position movement S1 to S2. So let's say we have an object is moving from position S1 and going to the S2. During that interval, the force is always perpendicular to the path of motion. Therefore, because this motion is literally not caused by that F, we expect that the force or the work of that force to be zero. We will see later that the definition of work is simply the force by the position displacement multiplied by the cosine angle, which is in this case cosine 90 and equal to 0. So the answer is 0. Second is if the particle is moved from 1 to 2, well, the particle is moving along a path, and that path is defined by S, and the particle is always on that path. The work done on the particle by the forces Fr, which is the resultant forces, so assuming the Fr over here is the resultant forces, which can be decomposed into components such as tangential component and normal, or you can use other decomposition depending on the coordinate system you're using. But for simplicity, it's always when you deal with work and energy, always look into the tangential forces, because tangential forces are the forces that causing the motion of the particle along the path, and will be easy to calculate the work, as you will see later that the work of a force like resultant force is going to be equal to the tangential, right, integration of the over the length. So the answer here is A. So the work of the resultant is, yes, we have two parts, but the work of the normal is 0, and the work of the tangential will be that part A. Great. Application, the roller coaster that you find in the amusement park has to be designed in a certain way that a cart or vehicles undergoing or going from a high elevation to another elevation must not lead to losing the cart from the rail. Especially when you go in flip motion, like point B, where we expect that if the rail or if the cart is in this position, and if it doesn't have any velocity, then the cart will free fall or will fall freely. However, because of the centrifugal force or centripetal force, which cause the reaction force of that cart to increase at this point, then that will hold the vehicle against or into that rail. So the question could be, to gain that velocity, or what is the minimum velocity required to maintain that cart in that position? And as we know, the higher the point A, the more energy or the more gravitational energy that kart system will have, as we expect that the velocity will increase as it's falling or as it's falling down. So the more height, the more velocity V will be. As simple as the free fall from high elevation. Or another application could be, for example, if you know the velocity of a vehicle approaching this barrel, how much is energy absorbed by this barrel, right? So that also can be calculated by the energy method. All right. So the work and efficiency, or I'm sorry, the work and energy is obtained by rearranging Newton's second law. We knew that the summation of all forces acting on a particle is equal to the mass by the acceleration of that particle. And by the chain rule, the acceleration can be written into the velocity dv ds. And so Newton's second law, we all know that if you have a particle, and this particle is along a path S, and you have here summation of forces, right, which is equal a resultant force. Let's say that this is the sum of it, and causing this particle to go from state 1 to another state 2. So this now the Fr is equal to the ma, and these are vector space. Fr is equal to the m dv over dt, or dv over ds, ds over dt, or dv over ds, and this is going to be v. So this is your v. So I can rewrite this so it's look like rearranged, where we put the v's and dv in one side and ds fr in the other side. All right, let me just, fr is the same as summation of forces, so for completeness I'm gonna just write it this way, dv, right? Now remember, these are all vectors, so this is a vector and this is a vector, and this is also a vector. Now suppose that we are interested to calculate the change in the velocity from 1 to 2. So this is state 1 and this is state 2. So I have to take the integral of these two sides. So what is the velocity change from v1 to v2, from state 1 to state 2? And that means also what is the distance as S1 and S2, right? And since this is an integration of vector, simply this could be later shown that we're only concerned because the integration of these two vectors will lead to, you can write it as S1, S2, summation of forces tangential plus summation of forces normal, ds equal to, I forgot here the mass. Now the velocity dv is simply equal to half v squared from v1 to v2, right? Great. Which mean, what does it mean? Meaning, this means, well, I'm going to decompose that into two parts. One, summation of forces tangential, and the other is summation of forces normal. And this is the path of motion, right? So the work of a force normal to the motion is 0. So we expect this to be 0, or let's say more correctly, ut ds from S1 to S2 plus the work of S1 to S2, summation of forces normal, un ds equal, I'm gonna simplify it, half mass v1 square, I'm sorry, v2 square minus v1 square. This is 0 because this is normal force, normal to the path of motion. We didn't expect this to cause any motion. So the only one left is the tangential, right? So we can say any tangent from S1 to S2, the summation of force is tangent, ut ds equal to half m v2 square minus half m v square, v1 square. I can rearrange and say, okay, it's equal half m v1 square plus S1 to S2 summation of forces tangent ut df, and in fact I don't have to put this because I already dropped the un, so it's a scalar quantity, so we know this is just a quantity, equal to the half mv2 square. So I just move this over here. Okay. All right. So I'm gonna call this is T1. I'm gonna call this is from U summation of all. I can take the summation outside. Summation of all the energies as it's going from 1 to 2, and I'm gonna call this T2. So I can summarize, this as T1 plus all the work done by forces that causing the particle to move from 1 to 2 equal to T2. So what that means is I'm going to go back here. It's going to mean that the T2, which is half mv square, and later we're going to call it the kinetic energy. This kinetic energy, which is the result of the velocity at state 2, is equal to the kinetic energy at state 1 plus all the work done on it as it's traveling from 1 to 2. So that's what it means. So this principle is called the principle of work and energy. So the principle of work and energy is that the work done by all the forces as the particle or system particle change their states from 1 to 2 or from one state to another is equal to the change in the kinetic energies, which is T2 minus T1, or you can write it in this form. Alright, so this formula is a scalar formula, so there is no vector required. And kinetic energy always positive because it's square of velocity. So it's just a matter of what's happening or how to calculate these, energies done by the forces, which will be the topic of the next section. Now, the units that we use to calculate the energy is joule or Newton meter. Now, notice that going back over here. Okay, so the unit of mass is kilogram, unit of velocity is meter per second. So this becomes kilogram meter square over second square. By rearranging, you'll find this is also equal to Newton meter, or we call it joule. Similarly, this equation, because it's a linear equation, and the units must be satisfied or must be identical. Therefore, we expect this also to be in joule or in Newton meter, which it is, because it's force by distance. So it's force is Newton and distance is meter. So it's a Newton meter. So you have different ways to express the units in SI unit. In SI unit, it's 1 joule equal 1 Newton meter. And the force pound second, it's feet pound force. All right, now let's talk about the different forces. So we have talked about the work done by the force as changing the state from 1 to 2, and that could be caused by multiple types of forces. An external force, like in this case, this F is an external force. And this external force can be calculated by, or the work of that external force can be calculated by F cosine theta ds. Now, some of you may wonder, where did you get this from? All right, so I'm going to go back one more slide and define you what is work mean. Now, a force does work on a particle when the particle undergoes displacement along the line of action of that force. So we define the movement of that particle from S1 to S2 by the component of the force along the action of the movement, which is the component of that force along the action of the movement, which is always tangent, and in this case it's F cosine theta, knowing that, assuming that theta is known, then that work is equal to, by definition, that component multiplied by the distance. So this is, by definition, is we're looking into it to the component of the force that causes the motion along the line of action or along the displacement. So that's by definition. So therefore, we are looking at this component. So this component can be extracted by knowing the angle theta. So in this case, become F cosine theta multiplied by that distance. Or if you're dealing with the vector space, we know that F cosine theta, it's simply the projection of that force on that angle, which means if this is tangent, then I'm looking at the dot product of F with ds. F ds, because the dot product between F ds is simply what? It's F cosine theta ds. So it's a similar way. Okay. So going back to the definition, if there is a force that causing an increment displacement from S1 to S2, and let's call it this as increment, then the differential work done by that force on that particle, which is du, equal to the force component F cosine theta multiplied by that ds. Okay, or by definition, the dot product, as we said, is equal to F dot dr, which will produce the F ds cosine theta. Okay, so that's in general, where dr is the position of that particle monitored in time. But for always dynamic, unless you are working with vector, that's your formula. If you're dealing with motion and non-path, this is your best formula. Now, if we have a particle that is moving along a rectilinear motion, or in a rectilinear motion from S1 to S2, and this force is Fc, then simply your work done on the particle due to the Fc is simply the displacement, because it's a linear, multiplied by the component of Fc along that line of action, or the line of movement, which is become Fc cosine theta S2 minus S1. And in this case, because you don't have any curvilinear motion, there's no need to do integral, because simply S is constant, meaning it's not changing with time, and F is constant, is not changing with displacement, and cosine theta is constant. So that becomes simple as that. So as long as this component constant, that becomes out of the integration, and then it becomes F cosine integration of S1 to S2, which is S2 minus S1. So that's, when it's both constant. So what does it mean to have a positive? So work is positive if the work and the movement are in the same direction, which is the dot product. So if they are along the same direction, then the dot product cosine is between 0 and 90, right? So meaning it's a positive between 1 and 0. And if they are opposite, then the work is negative, which means the line of action or the force is acting in a direction, but the movement is opposite to it. And opposite in the sense could be a component. If they are perpendicular, then its work is 0. All right, so far what we learned, just to summarize, so type of work. Actually, before that, I want to just emphasize on the principle of work and energy. We said that summation of all works plus T1 equal to T2. So I have two states, 1 and 2. I have, and I'm going to break it down now, two different forces, F1, F2, F3, and so on. Okay? And this is my particle that has a mass, and it's going from here to here. So these are the forces, or the work of these forces, and where U from 1 to 2, in simple form, for each one of them, for a particular force, we said it's equal to the force dot dr, or you can write it as F cosine theta ds from S1 to S2, or you can write it simply, I'm going to use this space, you can say it's equal to F cosine theta S2 minus S1, simply if these are constant. If F cosine theta constant along that displacement. Now, in case of external force, this is what you use, right? So is there any other types of work done by forces? So the first one is the external force, meaning that if I have an external force like that acting on a mass, and it's going from 1 to 2, then this will apply. So the force of that external is simply that, I'm going to keep it in general form, cosine ds, from S1 to S2, right, for simplicity. And it's a positive if the force, as we said, is along the movement. Another type is the work of the weight. The work of the weight. So what does it mean? So let's say I have a reference, which is the air. I have a mass, which has a weight equal mg. Let me choose my coordinate system to be y and positive in the upper direction. And I'm going to use this as my reference. And suppose that my state 1 is here and state 2, I'm going to make it curvilinear motion, so it does not necessarily linear. And my second state is over here, right? So it displaces by that magnitude. So this is delta y, where delta y is equal to y2 minus y1, where y2 is greater than y1, right? So delta y is, let's say it's moved from 1 to 2. So then the work of the gravity, which I can use the same, because we can say, okay, this is external force, so we can use that, is equal to this formula, mg cosine theta, and this is a vector that's always pointing down, ds, which will turn down to be, if you do the calculation, right, this is going to be equal to, now mg cosine theta can be written also as, well, I'm not showing, let's say here there's so many, it's equal to the weight dy from y1 to y2, from y1 to y2, and that's equal to the weight of the gravity of the weight, let's say of the weight, equal to w y2 minus y1. And here's the negative, right? Or negative w delta y. Meaning, what does it mean? It means that the work done on the particle, or the work required to move this particle from state 1, which is at lower elevation, to a higher elevation, is equal to negative the weight multiplied delta y, where delta y we said it's y2 minus y1, which is a positive. So this is a negative. This is a negative comes when delta y is positive. So we require this means we require additional work to move this particle from here to here. That's what it means. However, if I want to go from 2 to 1 of that weight, or of that gravity, then it's equal negative w y1 minus y2, where y1 is less than y2, so this is a negative value, therefore this becomes a positive value. So this becomes a positive value, meaning that the work done to move the particle from, or the mass from here to here is a positive, because simply it becomes w multiplied by that height difference, and meaning that there's no additional work should be added to make this movement happen. So this is important when you solve problems. So if you want to move a particle from lower elevation to higher, depending on where is your reference, because here we chose our reference to be below, then that force is a positive if it's going from high to low, and negative from low to high, or different states. Okay. Another type of work, this is continuation, so let's take another type, is the work of a spring. By the way, all of this you can see in the presentation file. The work of a spring. And this lecture is tend to be a little bit lengthy because there is some fundamentals you need to understand before we start solving problems. So when we have a linear, let's say a linear elastic spring, so this is linear elastic spring, okay? And let's for beginning is not attached to any external force. And let's suppose that this location over here is unstretched position. Unstretched position meaning there's no elongation from the normal position of that spring. And when you apply a force F, I'll call it Fs, I'm going to call it Fs, it's going to cause a displacement from, let's say, from this position to a new position. Call it S position, right? Now, we know that the force is going to be equal to K, linear elastic spring, multiplied by that S value, where S is measured from unstretched position. Now let's take a scenario, a general one, where I am moving the spring from position S1 to S2 as a result of a force Fs. Then, by definition, the work from 1 to 2, from this state to this state of that spring is equal. Is equal to what? We go back to the definition of the work Fs, right, dot ds, which is always along the line of action, so dot ds, or because cosine angle, or let me see, this is S1, S2, Fs, cosine 0, ds, this is 1, so I don't have to really put that, and this is equal to, now I substitute Fs value, which is Ks ds from S1 to S2, and this is equal to K half S S1 to S2. So the integration of S is half S squared, and then you substitute, so from 1 to 2 of the string equal, and I'll explain what that means, S2 squared minus S1 squared. Okay. So when a spring is stretched by a force Fs, the work of the spring, so this is called the work of the spring. This is very important. It's not the work of any particle. We're not talking any particle attached to it. The work of the spring force that causes the particle to move, causes the particle to move from position 1 to position 2, from S1 to S2, is given by that, right? Is given by that. Now, if S2 is greater than S1, then we expect that to be positive, and otherwise it will be negative. Okay, so this is the work of the spring force that causes the particle to move from S2 to S1. Now imagine, so now we understand what is that. Now imagine that this particle, same scenario, is attached to a mass, right? So, and I'm stretching that from This is the unstretched position, this is state 1 and state 2. Now, the Newton's third law says that the spring force which is causing this object. Okay, so this is the spring force Fs that causing this spring to move from state 1 to state 2. If there's a particle attached to it, that spring force is also, because of the because of Newton's third law, is equal in magnitude, opposite in direction. So therefore, we have a spring force Fs that is opposing the that is attached to the particle and opposite to the direction of the spring force. Therefore, the work done on the particle is going to be negative 1 from 1 to 2. Why? Because Fs on the particle is equal to negative Fs of the spring. So therefore this quantity will be, which will be computed from here, is the same, but the difference is that the work done on the particle by the spring, done on the particle by the spring, is going to be negative. So therefore, what we can write is the following. So done by the particle is equal to negative half k s2 square minus s1 square. So that's by the particle. I'm sorry, on the particle. On the particle. Done on the particle. Okay? Alright. So a couple of notation you need to keep in mind that the equation above is for linear spring only. So we assume that Ks is the force, but not necessarily all springs are linear, they could be nonlinear. So we have to do the integration if required. And also make sure that not to calculate the work of the spring by multiplying the Ks by S. In fact, you have to do the integration, which will lead to half Ks squared. Also double check the signs of the work of the spring. Positive work if the force on the object by the spring and the movement are in the same direction. Or think of it in different ways. Think of it as an energy sink and energy source. So if you're dealing with calculation of the principle of work and energy on a particle, now you can pump energy to a particle if that spring is tend to push and add energy, right? Or it could be absorbing energy if it is taking that energy from the particle. And I think it will be easier. I know a lot of you will be wondering if it's positive or negative. So we'll come over that, especially when you deal with many forces, you might make a mistake, but always double check, and I'll lead you to an easy method to double check. One more thing before we start taking examples is the work of a friction. Now, friction force is a force, but regardless, this friction force, in fact, whether it's along direction of motion or whether it's opposite, is always negative because it's energy dissipated. And in fact, even we know that the energy or the work of that force is the result of displacement multiplied the force, where the displacement and the force is always opposite to each other. So meaning that the energy is always negative. So in this way, we know the frictional force for this example is equal to the N multiplied by mu k, where mu k is the coefficient of, or the friction force coefficient, or dynamic coefficient of friction, not the static one. And when you multiply it with the distance, it's going to give you the work. So that's your work. So that's, you need to implement that if there is rough surfaces. So let's take a problem here and try to solve it. All right. So I'm, because of the time, I'm gonna solve one by hand, which is this one, and which might be slightly different depending on the references that you're using. So what do we have here? We have an object. This object is attached to a spring. Initially, at this instant, which is call it state 1, the spring is unstretched, meaning there's no external forces acting on the object by the spring. So there's no force Fs on that state. At that instant, the only external force acting on this object is the 100 Newton, and the kinetic energy, or the velocity of that object, is 5 meters per second. We know the mass, which is 10. We know initially the unstretched position, which is 0.6. And we know also the surface is smooth, no rough surfaces or no friction. We want to calculate the distance as when the block stops. So how long will this stretch until the block stops, right? Okay. So what that means, this means when is the velocity, stop mean when the velocity is equal to 0. Now, looking at that problem, the easiest way to solve it, because this problem involves distance, force, velocities, is to use the energy method. And more particularly, using the principle of work and energy. So, thinking of that, we can break down this problem into two states. A state 1, where it is right now at, and a second state is when the block stops. So when the block stops, we know the velocity is 0, but we don't know how much s. Initially, the first state, we know this is what is given to us. So let's move to the my notes and see how we can solve that. So the very first step is to draw the problem. And I'm going to choose also a reference. I know this is beginning. This is my S unstretched position equal to 0.6 meter, right? I'm going to call this state 1. This is where it's beginning. And this is state 2 when the particle will stop. What's required is to calculate this distance, right? How much is that distance? This particle, which is over here, at state 1, we do have many forces, including the external force, which is equal to 100. We also have the weight, which is equal to, we have 10 kilogram with the SI unit is 8.1 Newton, right? The force coming in the spring acting, because the spring is attached to it, and so it's tend to be pushing into that way. We don't have Fs here is 0, so there's no forces. Okay. All right. What happened here, from here to here, is this force will increase and it will cause the stop. Now, the good thing about the method of energy is it doesn't really care about what's happening in between, as long as that's included in the integration. I mean, actually, it's important, but as long as the principal of work and energy is correctly implemented, you don't really have to worry about what's happening here, what's happening here. Just, calculate that difference using the formula. I'm going to use a reference because the potential energy, or the calculation of the weight energy, requires a reference. I'm going to use this my reference. Meaning, I'm going to redraw this, or I can redraw it. Meaning that this object is moving from this state to that state and displaces by that magnitude, delta y, right? This is my delta y. So let's do some facts here. At state 1, the kinetic energy is equal to half m v1 square, and I can plug numbers, and the velocity was given 5 square, right? This kinetic energy. If this is my reference I'm using, then the work, okay, all right. The kinetic energy at T2, at state 2, is equal to half mv2 square, and this is equal to half tan 0 square, because it stops. Great. Now, the work from 1 to 2 is equal to the work of each individual force. So what are the forces we have? We have the work of spring plus the work of the gravity, because these are the only two forces acting on that object, gravity. Okay. All right. So what is the work of the spring as it's going from here to here? So we know that it's equal to, and I'm going to draw it again here just to make it clear. So we said this is state 1 and this is state 2, and this is my reference point. This 2, and this is unstretched position. So this is how much is stretching, right, before it stops. And that is, just for clarity, this is my delta y from here to here. For the spring is equal to half, right, k, and the distance traveled, which is, I'm calling it here, because I'm taking here a reference as s squared, right, or s2 minus s1 from the unstretched position. If you don't like this, I can do it this way. S2, if this is S2 minus S1, right? S2 minus S1, square. But I'm using S1 as a 0, and I'm using S2 as an S, just, and, for simplicity. I don't want to write S2 and S1. Okay? So this is the displacement. Again, S2 minus S1 square, S1 is 0, S2 is S in this case. All right. What about the gravity? Okay, so this, we assume this to be a positive quantity. What about the gravity or the weight? All right, this is my reference point, and the object is going from top to down, So the work is equal to negative W, right, delta Y, which is Y2 minus Y1. Right? Now, since this is my reference and it's going downward, y1 and y2, this is expected to be a positive value, meaning that I don't really need work. And this is where we double check, because the weight is sliding, right? You don't need any external force to slide it. Therefore, and I'm gonna, by the way, when you deal with weight, always positive is upward, right? So the y2 minus y1 is going to be negative y2 minus negative y1, where negative y2 is less than negative y1, so therefore this is going to be positive. If you don't like this analogy of discussion, you said, okay, whatever it is, it's a multiplication of the distance, which is delta y, by the w, but is it negative or positive? Then this is when you say, okay, the common sense says this is going downward, I don't need really energy to bring it down, so it's going to self-slide, so that must be a positive. So therefore, I'm going to say, okay, it's a positive, it's equal to the mg multiplied by the delta y, right? So with delta y is, and this is a positive value, no matter what you do, this delta y is equal to, so the angle here is 30, and this distance is s. We want to calculate for the s and remove anything that relates to delta y. So this is equal to the mg. Now sine 30, sine 30 equal to delta y over s. Therefore, delta y equal to s sine 30. So I'm going to here put s multiplied by sine 30. Sine 30 is a half, and mg is whatever value it is, right? So I'm going to put values here. So this is 10, 9.81 over 2 multiplied by s. Okay, great. So this is the only thing. So now apply the principle of work and energy between these two states, between state 1 and 2, which says, which we already written it over here. Oh, we haven't written that yet. So it says T2 equal T1 plus summation of all work from 1 to 2. T2 is 0, equal T1 is this value, half 10 by 25 square, oops, plus, now what do we have here? We have the first value, half k, k value was 200 by s square, plus this value we got here, it's 98.1 over 2s, right? So this is the quadratic form. Solving it, if you solve that, let's see, and we can simplify that. 0 equal to 5, 625 plus 100 s squared plus 49. My math is bad. 8.1, this is 90s, right? So you need, this is a quadratic equation, and you need to solve for s. And solving this will lead you to s equal to 2.09 meter. So this distance 2.09 meter. If you want to measure it with this reference, or if you want to measure it with this reference, you can just add this position, or this is from state 1, or if it's measured from that state, it's equal to 2.09 plus 0.6, which is equal to 0.69 meter. I know in the textbook they just plugged in a different reference, but I did that in purpose. All right, and second group problem solving. This is getting more interesting, but it's still simple. As when we use both the energy method and the information that we learned from the last two chapters, the kinematics of particles. But for the first part, let's take a look at the problem. This is in an FPS unit. So we have 2-pound force brick slides on a slope of, given with geometry given here, 3, 4, 5, and has initial velocity of 5 feet per second, the speed at point B, and also it asks you how much is that distance traveled from B to C. So there's two parts. How much is this D, and how much is this velocity over here? Before I start talking about the solution, so the easiest way to calculate, let's talk about the method first. The easiest way to calculate the velocity at B, since this is a smooth surface and this is just a change on the or the only forces acting on this body is its weight, so the energy method will be well suited for that, right? So so I will choose the energy method to calculate the velocity at B, knowing that the information of that object at A. So T1, which is half the weight, which is 2 over 32.2, multiplied by V squared, which is 25, is going to be equal to T2, which has half, right? Half what of mass, T, which is 2 over 32.2, multiplied by the unknown velocity, and the velocity is tangent to that, which is unknown, say VB squared, and the change is a positive as it's gone from A to B, so it's gaining velocity for the favor of T2. So we expect that this has to be done added to the T1 plus the amount of energy gained by the weight or the work done by the weight is simply the delta y by the weight. Weight is 2 multiplied by delta y. So from here to here is 15. So it's already given to us 15. So 2 by 15. So we have one equation we can solve for VB. So let's take a look at the details. So see, this is becoming much more, you're going to be, by practicing, it will be more efficient. And that's why we're having 2 over 32, because it's slug. Okay? And that's, we have unknown. Now this is tangent. So solving is going to give us the tangent value for that. Right. Now to solve for the speed of the C, I can use this state and that state and apply the same thing because I have the height now is different. Since this is smooth, so look at that. The only thing is different is I'm adding here the height, and you will expect the velocity to increase. This is in terms of velocity, but because another requirement of this problem is to calculate the distance d, this distance d, other things has to be done because we don't know how long it takes for that to travel from here to here. We only know that the component, x component of the velocity b, is causing this to travel in the x-axis, and that x component is simply whatever VB you found, which is 31, but in the x direction it's going to be multiplied by 4 over 5. And that 4 over 5 is the VBX, and using the equation of motion, we know that the distance is equal to the time of flight multiplied the velocity in x, which is VBX. So the distance traveled, I'm going to put it here. This is from equation of motion. It's 31.1 multiplied by the angle multiplied by the time it takes to travel from B to C. The reason why I applied that because we know there's no acceleration in or forces in the x direction as the particle goes from B to C. So therefore, this becomes a simple first equation or become a projectile problem. Now, to calculate D, I still need to know the time it takes to go from B to C, and that time can be obtained from the knowledge of the height. Now, given that I know the height, I know that the height at the beginning is 30 and at the end or at the beginning is 0 if this is my reference, and at the end is negative 30 if this is my reference point, right? And plugging into the equation of motion in the vertical motion y equal yb with the unknown and knowing the vby component, right? You have to be careful what we are plugging in here. This is vby. Then you have an equation, then one unknown, which is TBC. You solve for the TBC, which is the flight time from B to C, and that will give us 0.899. You plug this back in the horizontal motion, and that's going to calculate the distance d, which is 22.6 feet per second. Okay, so keep in mind that it doesn't mean that we always can find all the unknowns using one method. You always have to go back and implement what you have learned in the past. So with this group problem solving, we finish our first topic in chapter 14, and next lecture we'll take another topic, which is work and efficiency, on energy and efficiency, and I'll give you a bunch of homework to work on. By that time, we'll wish you the best. I'll see you next lecture.